Okay. Yeah, okay, should we start? Okay, so we're going to continue. Today we're going to discuss the problem about renormalization. So let me just record from last time where we are. Last time I discussed the following model, like say, for the toy model, we have isotropic splitting of a differential graded sympathic space for the toy model. And then from here, basically, we come to the following structure. We think about this V plus as the base manifold. And then this Q somehow is not compatible with the splitting. So in particular, it doesn't preserve V minus. So we write down the failure. And this failure actually is an element of symmetry 2 tensor, degree 1. And Q compatible, so Q closed. So these two data somehow are compatible, but this is what you wrote down from this splitting. Then from here, we obtained a DGBV algebra. This is a very natural like operation, and because like a P is like symmetry 2 tensor, this looks like a different like order 2 differential operator. So this is a B-way operator, and this is a differential. They are compatible, so anti-commutes, and all together they form a DGBV algebra. So this is what we were last time. But somehow I call this one toy model. So it's like we assume it's finite dimensional, so you can just do linear algebra. But actually, but from this data, I discussed some classical geometry and quantum geometry in terms of so-called B-way mass equation. So for example, we discussed what we mean by B-way quantum mass equation. So it's a solution of the following equation. So here, I somehow is a function on this V plus with quantum parameters. So something like that. I call it what? F? F? Okay. Great. So you read the notes. You have done the exercise. Okay, and if you send h bar goes to 0 in the classical limit, and this equation becomes the first order, like the leading term equation. This is a B-way classical mass equation. And I also explained some geometric aspect of these equations. So for example, this is basically about an odd version of Hamilton-Jacobi equation respecting this symmetry. I mean, this differential with the Lagrangian. And this is basically an element equation about this quantum gauge consistent condition. So this equation tells you like you can construct a Fock space in the Q cohomology class. Now, the problem in practice, so this toy model, but the real problem is like in real quantum field theory, we have to discuss like infinite dimensional case. And for this infinite dimensional case, some of the formal properties follow, but there's some essential difference and some essential difficulty. It comes from the infinite dimensionality. And for this infinite dimensionality, And we need to do some renormalization. So let me try to explain what's the issue and how to solve this issue. So that's why we discuss the renormalization theory today. Okay. So let me just lay down some basic structures following the same route. Okay, so in quantum field theory, I mean, this data somehow you have a space like differential gradient space. This space will be replaced by a chain complex. So I'm gonna write E, capital E for this one. It's space of fields. And usually, like this one has the following structure. It's given by like small sections of some kind of gradient complexes on a particular manifold, something like that. So it depends on how like the theory. I mean, this could be very complicated. Yes.
So are you excluding gauge series here? You're just talking about sections of bundles, or are you for connection, like for connection? Would that fit in there?
Yes. If for the connection, if you fix a reference point, I mean, the difference of the connection can be viewed as the like forms on some endomorphism bundle. So in that sense, so yeah, you can deal with like either connections or, for example, if you want to do like sigma model mapping space, you can modify this a little bit, but let's focus on this situation just for simplicity. Now, and Q somehow is a differential operator acting on this guy, differential. And somehow we require this operator to be elliptic. For example, this could be like coming from like D or D bar, things like that. And then in this sense, this pair will require this one to be in so-called elliptic complex. So that's one of the data that we start with. Now, for the other data, like we need this kind of this shifted sympathetic space and this P and things like that. So these are encoded by some kind of shifted Poisson kernel. So now from here, things become a little bit different. Like somehow this kernel is the inverse of some kind of a natural parent, geometric parent on the space of fields. The natural parent on the space of fields, say something like most of the time come from like integration. So the inverse of integration is going to be delta function. So basically this guy will be distribution valued. That's one of the starting difference with respect to the original case. So you don't have this kind of subtle topology on the infinite dimensional case. But here, it's not smooth section. It's a distributional section, usually supported by on the diagonal. But it could be other type of distribution. And I just mentioned like, so this P come from the inverse of like integrations. So it's like a delta function or some kind of derivatives of a delta function. So nevertheless, this again has degree 1. So no problem for this one, this degree 1. So it's a one-shifted Poisson kernel. So this is basically the data we have. Now we're going to start from here. Just follow step by step the towing model and see where we are obstructed. So we're going to follow the towing model. Let's do it step by step, and you will see where the problem is and what kind of thing we need to resolve the problem. So far it looks just natural and formal. Nothing serious happened because we haven't done anything yet. Okay, now step 1. Originally, we need to deal with like functions on our space. So for example, originally we deal with like the space and look at functions. So it's given by polynomial functions and things like that. So it's tensors of this kind of a linear function, so dual. So for finite dimensional vector space, the dual is very simple. But in our case, this field, like given by smooth sections. So this one has a natural topology. And the dual, this one is given by continuous dual. And we know continuous dual basically is called distribution. So this can be defined by distribution basically. So what we know basically what is the distribution, so we can talk about the linear dual. That's no problem. So at this moment, it's fine. Second, we need to talk about like say polynomial functions. So for example, let's talk about like quadratic functions. So we want to talk about say like tensors of these two. But for the tensor, it's also okay because we know how to take the tensor. It's like a nuclear space. We can take the like completed tensor product. So this is completed. So basically, this is the distributional sections of the bundle on the product space. So distribution on X product X. So this is also well defined, which is pretty okay. Nothing obstructs us for doing this.
So what's the difference between that and tensor E, the field of tensor? The field of tensor.
It's the same thing as box. Dual. Yeah. And so from here, similarly, we can define, for example, like symmetric n-symmetric tensor of this dual, like homogeneous n-degree polynomials on these functions. So this is like this you can define similarly for the nth tensor product. So this is given by like distributions on the nth product. And you look at just a symmetric subspace. So this is like a polynomial function on this space. And this is a graded symmetric product, as I mentioned before. So far, this is also okay. Nothing terrible happened. So we can define the same object as we called like functions before, like O, E. For example, I can define like formal power series on my space of field. So this is also well defined. So far, no problem. Now, next, we need to define this BV operator and this differential. The differential is okay. The hard part is this object. So we want to define this BV operator sending, remember, like sending originally in the toy model is something like that. This is for toy model. So this is like a second order differential operator. So it's supposed you have a degree nth polynomial. You basically contract with this like a symmetric 2 tensor. You kill 2 indexes. You get this operation. Now in the infinite dimensional case, this operation you still want to do the same object. And it is at this step which we run into trouble. This one is not defined. Because you see, like, first of all, this object are given by defined by distribution, and the P, the natural P that arises from this construction, is also a distribution. So you can pair a distribution with smooth data, but once you pair 2 distributions, you run into infinity. So we cannot pair 2 distributions. And this is a famous problem in quantum field theory, which is called ultraviolet problem, UV problem in quantum field theory. The reason is because like we are working with infinite dimensional case. So you have infinite many degrees of freedom. And because of that, you run into trouble. Like, for example, this infinite sum leads you to the singularity of delta functions and things like that. I mean, this problem arises in any models, like infinite dimensional models in quantum field theory. So we cannot define this operator, and so we cannot define quantum mass equation, and we need to do something. Okay. Now there are many ways you can do this. Like the standard notion of doing this is called like we introduce kind of renormalization. And again, there are different theories of renormalization. I'm going to introduce a very convenient model for doing this. In particular, in geometry, it's developed by Kevin Costello. I call this one Costello's homotopic renormalization theory. Okay, so let me explain the basic idea. I'm gonna somehow, for some purpose, I want to change notation. I apologize for this. Because there's something which will appear again, so I want to change the notation a little bit. I'm gonna replace this P by this K naught. I'm going to call this one the kernel P appearing here by K naught, and which is the element of a distributional section of this object. And this guy, as I call this one, shifted Poisson kernel. And this one is compatible with our differential and Q compatible. So this means like Q applied to K naught. The definition is like Q tensor 1 plus 1 tensor Q applied to this two tensor is 0. And this, because it's differential operator, this is like differential operator applied to distributions. This is well defined. So this is like a distributional equation. This still holds. So now I'm gonna erase this part, and I'm gonna use this K0 for my new notation of P. I really apologize for this. Okay. Now here's the key observation. First, I just wrote it down here, but let me just repeat. K0 is Q closed distribution. This is our starting data. Second, this is a step where all this the series of Castello, like how he started the whole framework, is basically this elliptic regularity. And this is a place where we require this to be a little bit complex. So basically, you can say the following: like, once you compute the cohomology for this elliptic complex, you compute like smooth sections. So the smooth data, the cohomology for the smooth data, and the cohomology for the distribution is basically isomorphic, the same. It's like, for example, if you want to compute the Ram cohomology, you can compute the Ram cohomology in terms of like distributional forms or occurrence, or in terms of just smooth differential forms, and things similar for D-bar and things like that. So this is the key observation. Once you have this one, you see like K0 can be viewed as a Q-closed object, so it represents an element in this cohomology. So you can use this data to move this singular object a little bit to make it smooth. So this means the following, means like they exist by distribution. So let me write it in such a way. So K0 can be written as the KR plus Q something. So now this guy is smooth kernel. And this one is distribution. But somehow make this equation holds. And this one also has a name. We know this from differential differential equations. We know this is called a parametrics, basically. So you can always find a parametrics such that you smooth out this kernel, and that's the starting point. And once you have something smooth, so you see like this is smooth, this is singular, and this is like basically equivalent up to homotopy. And then you can somehow study the original problem by this smooth data, which may be well defined, and study this homotopy explicitly. So let me try to tell you like what's happening. So let's put a name, like let's call this one KR. It's called a renormalized. B-way kernel with respect to the parametrics PR. Suppose let's just choose one parametrics. Then we can define the second order operator by contracting with the smooth kernel. And this is now well defined. Because now this is distribution, and this is like smooth things. So you can pair distribution with smooth object. This is well defined. So extend this one to like function ring, and you get a BV operator. Let's call this one renormalize the BV operator. This is again well defined. By the way, I work with formal power theories, and this is a perturbation theory. And so this process is basically perturbative. For non-perturbative theory, that's going to be very different, but let's focus on perturbative theory. And again, this is like a second order because like symmetric two tensor, so it have the same property. And because like original one is Q closed, this is again Q closed, so it's also compatible with Q. And the same argument tells us that this operator commutes with like Q like induce the differential Q on our function space. Then from here, now you come to the same data as we started from the toy model. So let's give this a name. It's like OE, Q. This BV operator, this is differential, defines, again, DGBB algebra. And called renormalized DGBV with respect to a choice of the parametrics. Okay, that's something we can define. And at this page, everything now is rigorous. Okay, but now you see from this this data, you might wonder like, okay, first of all, this parametrics is not unique. There are many different choices of parametrics, for example, and for each parametrics, you obtain such an object. And if you want to define quantization in this framework, you want to understand if you change the choice of parametric and how the whole thing change. So this is a basic question, like dependence on parametrics. So let's work it out. Suppose I have two choices of parametrics. So let's write down the equation. Like they both smooth out this kernel. Let's call the first one like QK1, QK2, like KR2, and by the second parametrics. And we know for different choice of parametrics, if you look at the difference, they differ by a smooth kernel. So denote. Let's call this one P R1, R2. Defined to be the difference of these two parametrics. And we know this one is actually smooth. And then we can, but it's smooth, it actually is a smooth section of this. It's basically the element of here. Literally, it's a smooth section of this bundle, and has degree 0. So we just define, because like an order 2 differential operator. Let's just define this this derivation in the same way as before. This operation applied to functions is a second order operator. By contracting with the smooth kernel. Defined the same way as before. Because it's now smooth, you can basically pair smooth kernel with this distribution. So this is well defined. Now let me tell you, like the real dependence of this DGBV algebra on the different choice of the parametrics. So it's given by the following proposition. The following diagram commutes. So it's basically the quantum complex arising from this DGBV. So for example, we work with like functions, like distributions on my space of fields with a quantum parameter h bar as before. Now, so first of all, like remember how we define the quantum mass equation. There's a combined differential acting on here is given by Q plus h bar, this B-way operator, for example, for the first regularization. And then I want to say, if you change the parametrics to different kind of like your operator here, like this kind of DG operator or B-way operator, will be train homotopic by a different operation. So formally, this is given by the following expression. So exponential h bar. So like this is a like order 2 differential operator. So this is like do power series expansion to this one, and so this operation intertwines the two different B-way operator. And this is a key proposition. So this means like this operation, which defines the quantum mass equation in the first Benzi's complex, if you choose different regularization, choose different parametrics, they are train homotopic by this operator. So that's the statement, precise statement. So yes, let me erase this part. Let's give a quick proof about this statement, because similar argument will be used again and again in many different places. It's a very simple observation, but very useful statement. Okay. So let's give a quick proof. Sketch. The reason is about this train homotopic. Basically, this formula says like KR1 minus KR2. If you look at the difference, equals Q PR1 R2. So this 2 kernel K differs by this P kernel in this train homotopic way. Then this implies the following: like it's a very simple exercise. Like this one tells you, like if you look at a commutator, gradient commutator of the Q differential with order 2 differential by contracting with the smooth kernel, it differs by contracting with these two smooth kernels. So This almost follows by just by looking, like it's a simple consequence of this fact. It's basically an equivalent way of rewriting the same formula. Then this one says that if you try to compute, for example, the conjugation, if you try to compute the conjugation, and we know if you conjugate some operator by this exponential, you can expand it in terms of commutators. The leading term is a q. Let me just write here. The second term is the commutator of this one with q. And because now this one is given by like constant coefficient second order differential operator. If you take the commutator with this one again, it's going to be 0. So that's all you have. All the higher brackets are 0 basically. And now you plug in this formula. You find like this q plus h bar partial k r1 minus h bar partial k r2. And this is basically the end of the proof. So you basically move this one to the other side, and that's it. So you have this object equals this guy. So you put this one here back, and you find that the conjugation of this q plus h bar, like the BB operator for kr1, conjugation by this operation is this operator, and that's exactly what we say here. So this operation intertwines these two chain complexes. This is the most important part so far. And once we have this, we can now construct and talk about quantization like in a precise sense. So let me just tell you what's happening. So first, let me explain a little bit about what this operator is doing, like exponential h bar, blah, 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 a second order operator. And we know actually, in quantum mechanics, we know whenever you see some second order operator, exponential of the second order operator, it's a version of integration. So, which is true. It's basically this Feynman rule, Feynman diagram expansion. So at the formal level. So let me try to say this precisely. And this operation is well defined on the following object. Say, let me denote it by O plus. Just to be precise. This is the object in this data. So let's look at this, the following type of functional. So this is like starting from one loop, h bar first order. So this is tree level. So this is says like this kind of object are those which are somehow cubic modular h bar. So this is like cubic action, like action cubic, at least cubic. Modulo h bar. And this plays the role of like, so in physics it's called the interaction theory. So any kind of interaction or some since you put on this vertex, something like this, like at least cubic, and then you can have quantum corrections. Then for this type of object, we can define an operation, this kind of operation, in a precise way. So this is called I call this one homotopic renormalization group flow equation. Yeah, or in the original like work of Costello, he used the name just renormalization group flow, but it's a little bit confusing with the physical renormalization group flow equation, which is about the flow arising from the rescaling argument. So it's better somehow to call this one homotopic RG flow. I'll tell you the reason later. So roughly speaking, this is I use the same notion as what Kevin used, as W P. It's an operation acting on this object, the space of interactions. In terms of formula, it looks like sometimes we write apply this operation to some kind of interaction term. A definition is given by h bar log e to the h bar, the second order operator, and apply to e to the I over h bar. So I is my interaction term. So this is like you put this I to be this exponential form and apply this exponential of the second order operator, eventually take a log. And this is a formal expression, but actually this one looks like you might wonder like how much this is well defined and things like that. This is actually well defined on the space of interactions. And here's an exercise for you. If you haven't seen this before, so the real content of this formula is like if you write in a different way, it's like left-hand side is e to the w operation, whatever this one is. The left-hand side, if you just take the exponential, equals this kind of object applied to this actual functional. So this literally is a result of applying this operation for this exponential factor. And now from here, you can, again, this is formal. Now from here, there's a way to rewrite this equation, formal equation, in terms of combinatorial equation. And this is the final answer is given by like Feynman diagrams. There's a combinatorial expression, like sum of all connected graphs, some kind of Feynman expansion. And this like gamma looks like, suppose you can write something like that. And once you write down some kind of kinetic graph, you put this kernel P on the edge as a propagator, and the original interaction is something you put on the vertex. And that's how you evaluate this kind of Feynman graph. At the external edge is the input, so it's like this is distribution valued. And you can check. And probably some combinatorial factors I didn't write. It depends on how you define this object. And you can check the sum of all these kind of connected graphs is a well-defined operation on this space. And that's the real content of this formula. So in short, like this is what physicists would call like a vertex. And this is what physicists would call a propagator. And this is the real content of this formula. And if you haven't seen this before, like it's better to do this exercise. And I have a lecture video on my Billy account to explain this if you want to take a look. Yeah. Okay. Yeah, that the video on the Billy was somehow produced in preparation for this lecture series. So. Okay. So finally, I can talk about once we have this notion, and once we understand this operation, chain homotopy, by these Feynman diagrams, and we can now write down a mathematical definition of this like quantization precisely. So a solution of effective quantum mass equation. So we don't have this notion for the toy model, and this is a notion that I write from this infinite dimensionality. Is an assignment maybe I wrote it wrong. Assignment. Let's call IR of this object is basically a family of interactions parameterized by some regularization for each parametrics. PR satisfying the following property. First, it's like once we choose the regularization, this parametrics, we have a DGBB algebra. Once we have DGBB algebra, we can write down the quantum mass equation. But this quantum mass equation depends on the choice of parametrics. So let's call this one renormalized. Quantum mass equation. And or RQME. By this following equation. So it's the equation in this DGBB algebra. Q plus H, let me write here, Q plus H bar with respect to this smooth kernel applied to this object, regularized interaction, this has to be 0. This is the analog of this quantum mass equation that we discussed in the finite dimensional toy model. Now this is well defined for distributions and smooth kernel. Now you see, like, you want to ask, oh, I shouldn't erase that part. Let me. The second one is to show that if you choose different choice of this regularization, they're related by this homotopic RG flow. So for any kind of two parametrics, like PR1, PR2, that this different choice of this interaction are related by this homotopic RG flow by this equation. So these are related by this equation. And I shouldn't have erased this part. So remember, like, this kind of equation, like the chain complex, I just erased. So it's like by previous proposition, we know, like, if you apply this kind of quantum B-wave operator, and then you do this chain homotopy by this propagator, or somehow around this Feynman diagrams, is the same thing as this object. By applying the quantum B-wave operator in the second regularization, this is the previous proposition, this chain homotopy. So by this proposition, you see, like, the condition 1 and 2 are compatible. So there's no strange thing happening. Like if you satisfy this quantum mass equation at one localization, by this choice, you satisfy the quantum mass equation on the other localization. So the picture is like, originally you have this kind of space. At the original point, 0, everything is very singular. You don't know what to do, and you have a singular
Choose I to be 0.
yes, localization. This is like no localization. This point is like ill-defined. Then you basically you localize this at some point. You solve some equation, or you localize a different point, and they're related by some kind of RG flow, homotopic RG flow. And this definition shows that it doesn't depend on where you move. Like as far as you do this one consistently, like at the commutator level, it's basically the same. So this is similar to, you know, like in algebra geometry, we want to define, for example, like a residue. At the original point, it's very singular, you don't know what to do, but you deform the singularity a little bit, it becomes a bunch of like Morse type singularities, and you can define residues there, but then this residue is independent of choice of how you perturb the singularity. That's very similar to that picture. So, but here is on the framework of quantum field theory. So I think I'm gonna stop here and continue after the break.